Hello, Glendale Community College. We are still talking about solutions. So I have another question about like dissolves like, which again means that polar mixes with polar, nonpolar will mix with nonpolar, but polar and nonpolar will not mix. So here we go. The question is, will these solutes dissolve in the given solvent? We're going to go across the ammonia row first. So ammonia, NH3, is going to be our solvent. Now we have to think, is NH3 polar or nonpolar? For that, you may need to do a Lewis dot structure. So hit pause and do a Lewis dot structure if you can. And we're back. Maybe you remember ammonia from another time, or maybe you did the Lewis dot structure, but it is in our shapes table a trigonal pyramid molecule with a lone pair on top and 3 atoms bonded to it. So it's not symmetrical. So those polar bonds, the NH bonds are polar, do not cancel out with each other. So the molecule remains polar. So it's polar. All right. Will HCl then mix with it? Yes or no? HCl is 2 different atoms, non-metal atoms. So that bond is polar. So polar and polar will mix, yes. All right, will iodine mix in with NH3? Will it dissolve in there? Well, I is bonded to itself, I to I bond, I2. So is that polar or nonpolar if you're bonded to yourself? Nonpolar. So will these mix? No. Nonpolar and polar do not mix. All right, PCl3. We did this one earlier. It was also a trigonal pyramid structure. Looks like that with the lone pair on top. It is also polar. So will these mix? PCl3 in ammonia. Yes, polar will mix with polar. What about CH4? We talked about this. CH compounds are always non-polar. Yeah, so will those mix? No, they will not. All right, next row. C12H26. It's a hydrocarbon. It's a CH compound. What did we say about all CH compounds? They are non-polar, non-polar. So would HCl mix with it? No, because HCl is polar, so those won't mix. Will iodine mix with it? Yes, because both of those are non-polar. They're both non-polar. Will PCl3 mix with C12H26? No, because that's a polar non-polar combination, so those won't mix. What about CH4? Will that mix with C12H26? Yes, because they're both hydrocarbons, so they are both non-polar. Non-polar will mix with non-polar. The last column is bromine, Br2. That's a liquid. So Br2, Br with itself, Br to Br. Is that a polar or non-polar bond when you're bonded with yourself? You're correct if you said non-polar. So will HCl mix with it? No. Will iodine mix with it? Yes, they're both non-polar. Will PCl3 mix with it? No. What about CH4? Yes, because they're both non-polar. Okay, so again, this is all about like dissolves like. Polar mixes with polar, non-polar mixes with non-polar, but polar and non-polar will not mix. All right, moving on. The dissolving process. So solvent molecules pull the solute molecules away from each other if it dissolves, which means the solute solvent attraction is greater than the solute solute attraction. What does that mean? Okay, so in the case of salt dissolving, we have NaCl, right? that ionic bond between Na plus and Cl minus is pretty strong. But if you put salt in water, a bunch of water molecules can go up around the sodium and the oxygens can point in and create all those solute solvent interactions. Again, it's called the ion dipole force here between the sodium and the oxygen, the sodium and this oxygen, the sodium and this oxygen, and so forth, with a bunch of oxygens pointing in towards that sodium. And all those attractions are stronger than that ionic bond, so it actually will break apart. Now, remember, not all ionic compounds are soluble. You have to check the solubility rules. But that's basically what happens when something dissolves is we create these new intermolecular forces. There's multiple of them, and together they can overcome that solute-solute attraction, and so the solid will dissolve. So we have these interactions that form between the ions and the water molecules when we put an ionic solid in a aqueous solution. If we have nonpolar solutes and solvents, then London dispersion forces form between them. So again, here's a picture of solid NaCl. We have the NaCl, NaCl, NaCl ions repeated in that crystal structure there. The water molecules come up and the oxygens point inwards towards the Na plus, and the hydrogens point in towards the Cl minus, right? Because opposites attract. Cl is negatively charged. The hydrogens are a little bit positive, so opposites attract and the hydrogens point in towards the Cl. Again, this is the ion dipole forces that we talked about earlier, and it's why things dissolve. We call this process solvation. All right, moving on. Concentration. Concentration measures how much solute is in the solvent or the solution. If it's concentrated, that just means there's a lot of solute per solvent. If it's dilute, it means there's not a lot of solute per solvent. So we can see this picture above me. We have diluted solution towards a concentrated solution of, I think it's just cranberry juice with water. But we can see what we mean by dilute. There's not a lot of solute, and concentrated, there is a lot of solute for that solvent. So there are different ways to calculate concentration and give a number to it so we can quantify it. That's important. We're going to learn two ways in this class, mass percent and molarity. So let's go ahead and learn about mass percent first of all. This is used in hospitals for like saline solutions, the IV bags that the medications are given in to you intravenously. So mass percent you will see in a hospital. So mass percent is one way to measure concentration. It's a way to express the amount of solute in a solution. Now remember, a percent is always part over total times 100. Part over total times 100. So a mass percent is going to be mass of the solute, which is part of the solution, over the total mass of the solution times 100. So again, it's part over total. Now what you have to remember is the total mass of the solution means it's the solute plus the solvent mass together. So you have to remember the total solution is solute plus solvent, not just the solvent. That's part of the solution. The solution is the whole thing. It's the solute and the solvent together. You have to add them together for the denominator. All right, let's look at an example. Calculate the mass percent of a solution that contains 15.0 grams of potassium nitrate dissolved in 135 grams of water. We want mass percent. Mass percent is mass of solute over mass of solution times 100. Notice this is actually on your shapes table. So you can go look at the back of your periodic table and see this formula. So let's look at these 15.0 grams of potassium nitrate and 135 grams of water. Which of those is the solute? It's the one there's less of, right? So that would be the 15.0. Now that's the top number. What is in the bottom mass of solution? Is it 135 grams? No, it's the solution, not just the solvent. It has to be both things added together. So it's going to be the total 15.0 plus 135. That's what's on the bottom. So mass percent equals 15.0 grams in the numerator over 15.0 plus 135 grams in the denominator. Make sure you add those first. Then divide, then multiply by 100, and we get 10.0% because we need 3 sig figs. Everything had 3 sig figs. All right, that's a very typical mass percent problem. You need to practice more of these by looking at your worksheet and end of chapter problems. You will definitely see mass percent again. All right, see you in the next video. Bye-bye.